Now, it looks like a diffraction pattern, but you know that in order to get such a thing, two conditions have to be satisfied. First of all, we have to have a random array of cross gratings, and we also need some radiation that has a well-defined wavelength. Well, it's not difficult to see how the first condition is satisfied, because graphite has a crystalline structure. It consists of these regular arrays of atoms, all in a line, and indeed we can draw a set of parallel lines through them, as you can see here, with equal spacings, so that would constitute a grating. And moreover, these same atoms belong to other sets of straight lines, like this one here, and so it actually is a cross grating. And with that foil of graphite, we have a great many very tiny crystals, so we get a random array of cross gratings. So, if this is a diffraction pattern, then it means that the electron beam has to have a wave-like nature as it passes through that target. It has to have a wavelength. And we can actually measure the wavelength by measuring the diameter of the rings and by knowing what the spacing of the atoms is. Now I want to show you something interesting about this pattern and the wavelength of electrons. You remember I said that the electrons were accelerated by that high voltage plate. Well, with this device here, I can adjust the voltage and therefore adjust the energy of the electrons. So as I change the voltage on that plate, I want you to observe what happens to the diffraction pattern. I think it's probably best if you concentrate on one of those rings in particular. So here we go, starting off at about 2.4 kilovolts and going down. That's 2.0, 1.5, and down to 1.0 kilovolts. As you see, the pattern gets larger the smaller the voltage. Let's just go back up again, give you a chance to see that again. Going up now, back up to 1.5, 2.0, and finally 2.4 kilovolts again. Okay, so as the voltage goes up, the pattern goes down, which means that the wavelength is decreasing as the voltage goes up. And so it turns out that there is a very simple relationship which connects the wavelength with the energy of the, of the electrons. Actually, one uses the momentum, and this is the relation. It's called the de Broglie relation. It connects the wavelength lambda with the momentum p, and the connection is made via Planck's constant h.
Perhaps it surprised you just a bit to see electrons behaving like waves. But were these diffraction patterns really produced by electrons? Well, there's one surefire way of checking that. We're deflecting the electron beam after it's come through the graphite target with a magnet. So the electron beam is interacting with the magnet, behaving like particles. So in the same piece of equipment, we've demonstrated both wave behavior and particle behavior.